Hi, my name is Neha. I am Triple E graduate student at California State University, Sacramento. I am going to talk about emerging technology in the area of semiconductor manufacturing called 3D IC with NFET and PFET on separate layer using gold or silicon dioxide hybrid bonding. These are the topics that I will be talking about throughout the video. First, I will start with a brief introduction about 3D IC, followed by motivation of 3D IC and process of 3D stacking, fabrication technology, 3D CMOS inverter, advantages of 3D IC, ideal application of 3D IC, and finally the conclusion. 3D integration of CMOS ICs is expected to deliver a breakthrough beyond the scaling limit of conventional 2D CMOS ICs and a higher circuit density. More than multifunctional diversification has found increasing significance in 3D IC technology to achieve high-density CMOS circuits for various applications, such as sensors, actuators, radio frequency devices, and microelectromechanical systems. Basically, a 3D IC is a three-dimensional IC built by vertical stacking different chips or wafers together into a single package. A 3D ICs have a potential to dramatically enhance the chip performance, functionality, and device packaging density. There are various approaches for 3D integrations have been reported. TSV through silicon wire technology is the most mature, but it is not always suitable for large wire size of typically 5 micrometer and more. TSVs are based on the sequential integration and silicon on insulator assembly are promising for high density integration. However, penetrating wire for interconnections are required outside the FET areas, which limits the density and free wiring layout. The density degradations come from the conventional process that leads through SiO2 wires and metal wires after stacking device layers. Beside the demand for high-density integration, today advanced CMOS process requires delicate process tuning of strain, crystal orientation, and channel materials for each of NFET and PFET, and it is becoming difficult to pursue best performance of NFET and PFET on same wafer. It would be preferable to accommodate NFET and PFET in separate wafer and bond them by 3D stacking. To overcome this problem, we propose a 3D integration method by using the low temperature direct bonding with a hybrid material of gold and silicon dioxide. Apart from the conventional bonding method, this method permits direct connection between FETs on separate wafers after the completion of process including metal interconnection. FETs are aligned and bonded by surface without using an additional area, thereby attaining the suitability for ultra-high density integration. Process optimization for both NFET and PFET processes is possible because both the FETs are prefabricated in different wafers. In this slide, we are talking about the proposed 3D stacking process by direct wafer bonding. Fully depleted silicon on insulator wafers of NFET and PFET with metal wires are directly bonded on SOI surface as shown in figure A and B, which is followed by the backside electrode process reported in figure C. Owing to electrical conductance of fully depleted SOI and minimize the interconnect length between the mated FETs, the output current can be obtained from electrode formed through buried oxide layer without attenuation. The subsequent process of bonding and backside electrode forming provide the multi-layered 3D IC as shown in figure D. In this, we will understand the fabrication process of direct bonding. There are few steps of fabrication process. First is FET and aluminum electrodes are formed on SOI wafer as shown in figure A. The thickness of SOI and gate oxide are 50 and 4.4 nanometer respectively. The intermediate SiO2 layer is patterned and etched to form the wire holes to embedded aluminum electrode. A seed layer of titanium or gold is deposited by sputtering, and a gold layer is formed by electroplating as shown in figure B. The demising process by chemical mechanical processing is applied to form a flat surface of gold or silicon dioxide in figure C. The chip surface is activated by argon plasma and oxygen plasma before bonding the process. Here, argon plasma is used to physically remove the contaminants, and oxygen plasma is used to remove the organic contaminants and to create the OH group on surface to increase the silicon dioxide bond strength, as shown in figure D. There are two chips are aligned using an infrared microscope and directly bonded at a force of 2000 Newton for the 60 minutes under low temperature of 200 degrees Celsius in figures E. Here is one example of direct bonding process. In this CMOS inverter, in the figure of 2D, NFET and PFETs are on same layer and connected side by side. However, in 3D figure, NFET and PFETs are on separate layers are directly connected, which reduces circuit footprint and enable the independent optimization of NFET and PFET process. This plotted graph is about the drained current as a function of gate voltage measured on zero point 0.2 micrometer gate FETs before the bonding. The subthreshold slope of any FET and PFET were found to be very close in the millivolt per decade respectively. This graph shows the transfer characteristics measured on 3D CMOS inverter bonded through the 3 micrometer diameter gold electrodes. For comparison, the same figure also plotted the characteristics of the CMOS inverter flattened in a single chip by the same process, which is 2D. Owing to the identical characteristics, we conclude that the bonding caused no degradation in the IC performance. The developed 3D ICs are considered to have the following advantages. First is high density 3D integration. Due to FETs are directly connected within the size of transistors without an additional area for interconnects. Second advantage is it does not degrade the IC performance. That is due to the direct bonding is performed at a low temperature of 200 degrees Celsius after the completion of FET process. The third advantage is higher performance as NFET and PFET fabrications are performed in a separate wafer layer, thus they could be optimized independently. Wafers of a different crystal orientation and materials are chosen to make ideal channel design for both NFET and PFET, leading to a higher performance of a 3D IC. The fourth and fifth advantages, high speed operation and low power consumptions are happen because of the SOI FETs having a feature such as a very low parasitic capacitance, small body effects, no latch up and small junction leakage. Ideal applications are data center, mobile devices, cloud computing, Internet of Things, and a high performance computing areas. 3D ICs made from NFET and PFET on separate wafers were successfully understood by applying the gold or silicon dioxide hybrid bonding. Measurement graphs of the fabricated 3D CMOS inverters confirmed its characteristics to be identical to those of 2D circuits, indicating the feasibility of 3D IC. The result enforced that the 3D ICs made from a lot of separate layers could be operated with the successive direct bonding and the backside process. Since the 3D ICs directly connected the FETs without an additional area for interconnects, they are suitable for ultra-high density integration. Owing to the separate wafer before the bonding, the process can be optimized for NFET and PFET to improve the IC performance. In conclusion, The developed technology is promising for realizing high density and high performance next generation large scale integration.